We have been discussing the pendulum equation in the past two videos. I think video 21 and 22. We set up the pendulum equation, and this was the final form that we obtained so far. What we need to do is solve this integral. If we can do that, then we will have a solution for the pendulum that is good for all angular displacements, not just small angular displacements that you see those kind of solutions in most textbooks. Reminder, the playlist for the videos is at the website digital-university.org. Now, to solve this integral, it's going to involve elliptic functions, and elliptic functions in trig form are these two general forms. Again, if you go to the website at digital-university.org and click where it says free calculus videos and then scroll down to where it says integral functions, you see we have videos dealing with the gamma function, the beta function, and with these types of elliptic functions. Now remember, from those videos, k has to be a fraction. The maximum value theta can have is pi over 2. And as we can see from looking at the formulas here, they involve sines, not cosines. So we have to go back to here and get sine expressions down. So we remember the old trigonometric identity that the cosine of theta, actually let's make some more room here, the cosine of theta is like 1/2 or 1 for one of its forms. It equals 1 minus 2 times the sine squared of theta over 2. So for the cosine of theta minus the cosine of theta max, we're going to have 1 minus 2 sine squared of theta over 2. That's the cosine of theta, minus 1 minus 2 times the sine squared of theta m over 2. So that's cosine theta minus cosine theta m. So let's see how this works out. We have 1 minus 1 minus negative 2. This becomes positive. So we have 2 times the sine squared of theta m over 2 minus this negative term, 2 times the sine squared of just theta over 2. Remember, theta m, that was our maximum angular displacement for the pendulum. Okay, so now we can put this up here in place of this, and we're going to have a 2 inside a square root sign. We can factor it, take it to the outside, so then we'll have 1 over the square root of 2, and then inside of here we're going to have this minus this. So we have sine squared theta m over 2 minus sine squared theta m. So our equation now looks like this, and let's make some room. Now, for the sine squared of theta m, that's our maximum displacement. So this is just some constant number. So say for the sine of theta m over 2, just call that k. And then the sine of theta 2, oops, we have theta m here, that should not be there. This is theta over 2, and this is theta m over 2. Okay, now we have it in correct form. Except this should be m here, not here. Now it's in correct form. Sine squared theta m over 2 minus the sine squared of theta over 2. Okay, now, so the pendulum is swinging. Then it reaches its maximum displacement and then swings back in the other direction. So the sine of theta, this term right here, the largest value this can have is when theta becomes theta m. So the sine of theta 2, or the sine of theta divided by 2, that's less than or equal to the sine of theta m over 2. And we're calling this k. So we can have it like this. So this either equals k, the maximum displacement, or it's going to be some fraction of it. So we could write it like this. We could say that the sine of theta 2 equals k, say, times the sine of phi. Why can we say that? Well, first of all, remember that when we're setting up an elliptic integral, the maximum value this can have is pi over 2. So we're dealing here then where the sine of an angle is either 0 or it's 1. And we're saying here that this is less than or equal to k, so this either equals k times 1 or k times some fraction. And that's what this is. This is either 1 or it's some fraction. So this is just another way of expressing this. So if we use that substitution and rewrite our integral, we also have to think about how these limits here are going to change. And actually, this is not theta. It begins like this. Theta equals 0. Then it goes up to theta maximum. So let's look at here. What we're going to do then is, for the sine of theta 2, of theta over 2, we're going to call it this. Make that substitution. If we do that, then what will be the new limits? So theta, that goes from 0 to theta maximum. Now what about psi? Or actually not psi, but phi. Okay, let's see how this works then. We have the sine of theta 2 equals k times the sine of phi. Well, if theta is 0, that's 0. So then this has to be 0. So that is 0. Now, when we have theta m, that's our maximum displacement. So that is theta m. So then this has to be 1. Let's see why that's so now. We're saying that the sine of theta over 2 is less than or equal to k. When we have the maximum angular displacement, this becomes theta m. that's k. So then this has to be equal to 1. And the sine of psi is, at pi over 2, is 1. Let's just review that one more time. Theta goes from 0 to theta m. When theta is 0, the sine of 0 is 0. This is going to be 0. When we have theta m, then this is now theta m over 2, which is k. So when we have theta m, when it goes to here, this is theta m, that has to equal k. This has to be 1, and the sine of pi over 2 is 1. So if theta goes from 0 to theta maximum, psi goes from 0 to pi over 2. So those will be our new limits once we make this substitution inside of the integral. Now let's look at this further. So we're saying that we're using this substitution. Remember that we're going to need space. Remember what our new limits are. They're going to go from 0 to pi over 2 once we start making this substitution inside of the integral. Because we're going to erase this, we need the space. So we have the sine of theta over 2 equals k times the sine of psi. Now we take derivatives on both sides. The derivative of the sine is the cosine, so we'll have the cosine of theta over 2 times the derivative of this with respect to theta, that will be 1/2 d theta, and that will equal k times the cosine of psi d psi. Now what we want to do is replace d theta so that it's expressed entirely in terms of our new substitution here, psi. So the way it stands right now is we would say d theta will equal, multiplying both sides by 2, we'll have d theta will equal 2k times the cosine, that's just phi, we keep calling it psi, that's phi, divided by the cosine of theta over 2 d phi. But now we have to express this in terms of phi. Then we'll have d theta will be expressed in terms entirely of our new substitution here, phi. So how can we do this? Well, this, of course, the cosine of theta over 2, that's the square root of 1 minus sine squared of theta over 2. But now we have to go back to our substitution. The sine of theta over 2 was k times the sine of phi. So this equals square root of 1 minus k squared sine squared phi. So we can substitute this right here where it says the cosine of theta over 2. So let's do that. So this is divided by the square root 1 minus k squared sine squared phi. this anymore. So now, let's write this a little bit neater. Square root 1 minus k squared sine squared phi. So now d theta is expressed entirely in terms of the new variable phi. So this is now this. So let's go ahead then and start putting substitutions into this integral right here. So here, notice we have 2, so we'll take that to the outside. Remember, we had 1 over the square root of 2, so we're going to have 2 divided by the square root of 2. Then we have this integral, and the new limits, remember, we're dealing now with psi, and that went from 0 to pi over 2. And then d theta is this, and here then we have sine squared. Well, that's going to be, this is k squared minus k squared sine squared phi. Okay, this is this term with our substitution. K squared is this. This squared is going to be k squared sine phi squared, which we have written right here. And we had a 1 over square root of 2. That's here. Now, from the d theta term, we have this. Then we also have k. The 2 is out here, times the cosine of phi. Then we have this term. One minus k squared sine squared phi d phi. So here then, let's just go back. We started with this integral. We made this substitution, which followed into this. And then finally, that transformed this integral into this integral. Now notice we can factor k squared out of this, but this is just going to be then take the k to the outside, and we have 1 minus the sine squared of phi. Of course, these k's cancel. This is the cosine of phi, which is what that is. So this and this cancel out, and the only terms left in the integral then are these two. So let's do this. I don't need this any longer. And 2 divided by the square root of 2, of course that is the square root of 2. So we have this. So our integral then is just d phi divided by this. So let's write it like that. So we have d phi divided by the square root of 1 minus k squared sine squared of phi. Now, let's go back to the top of the page for a moment. This integral, which we have entirely rewritten, was equal to this expression. That's the period divided by 4. We derived that in our previous videos here. So let's put this down here. Before we were writing this as a capital L, that's the length of the pendulum. We now have this expression. Originally, the length of the pendulum we called capital L along the way. We changed it to short L, but it means the same thing, the length of the pendulum. But now here is our equation, and notice that this is an elliptic function. It goes from 0 to pi over 2, 1 minus k squared sine squared phi. Remember what k is? It's this. So the maximum value that this could ever have is 1. So this falls between 0 and 1, meeting the requirements for an elliptic function. Now, most elliptic functions cannot be evaluated in terms of simple functions. You have to look them up in a table of integrals or table of values for your particular integral once you get into this form. However, this one we can evaluate, and we can do that by considering this denominator in more detail. We won't have time to do that in this video. What we'll do in the next video is we're going to come back. Well, in this video, we went from this equation to this equation where we now have an elliptic function. Now what we're going to show is that for this particular type of elliptic function, there is a solution for it in terms of elementary functions. And to see what that solution is, that we'll consider in the next video. So come back, join us for that video, and we're going to work further then with this elliptic function.